is Nezamabadi from Chalmers. Take it away.
Yes. Hello. My name is Daniel. I'm actually a master's student at ETH Zurich, but today I'll be talking a bit about the work I did with Magnus at Chalmers in a summer internship, which was creating a CakeML backend for Dafny. So I hope everyone knows what Dafny is at this point, but in short, Dafny is a multi-paradigm programming language, which is verification aware, meaning you can write your project in object-oriented style, functional or imperative style. But you can also add pre and post conditions to, for example, your methods. So you can write some precondition, and assuming that's true and you execute the code, the post condition will also be true. So if we assume you go through the trouble of implementing everything in Dafny and writing down specifications, proving them correct, which Dafny hopefully takes care of mostly automatically, we'll probably want to run your Dafny code. And the way this works currently in Dafny is you actually translate this to some higher language like Java, Python, C#, and then use those languages as toolchain to actually execute that code. There's a slightly new way, it's mostly technical, where the Dafny code is first translated to something called the Dafny IR. That's what I call it. It's you can imagine it as like a kind of a desugared form of Dafny. It's not quite. It's mostly some technical stuff. And then you go from this Dafny IR to, for example, Rust. I think that's what the Dafny team was working on. I think there will also be a talk on this. And then you can, for example, use Cargo or the Rust compiler to actually execute the code. Now, the issue with all of these things is that all of these steps must be trusted. So they're part of Dafny's trusted computing base, and we can roughly split them up into two parts. One is, for example, you need to trust Java compiler, the Rust compiler, the Python interpreter. But on the other hand, you also need to trust everything on the front end, kind of, if you want to call it the front end, which is going from Dafny to the Dafny IR, or just going from Dafny IR to the high-level language like Rust, or from Dafny directly to Java. And I think there's actually also another talk, which is testing the whole end-to-end pipeline, and I think some bugs were actually found somewhere in this case, but I might be wrong, so make sure to watch that talk. So what is our proposed solution? Well, before we get to that, I would like to talk a bit about CakeML. So what's CakeML? I think there's two ways you can actually think about CakeML. One being it's just a subset or like a verified subset of standard ML. So it has its compiler with a bunch of intermediate languages which go down to machine code. Or you can think about CakeML as more the project. And if you do that so you think of CakeML as a project, you will also have things like Pancake, which is like a language roughly on the abstraction level of C, which targets the lower parts of the CakeML compiler. Or you have, for example, PureCake, which is a very much Haskell-like language that translates down to CakeML, which is something similar that we will be doing. We'll take Dafny and compile it down to CakeML. And what we'll also be using, well, we won't be using PureCake, but what we will be using is this step where we can go from functions in whole, so higher order logic, down to CakeML. And what we'll be using here is we'll be writing our compiler actually in whole 4, our theorem prover. And then we have the CakeML translator, which extracts essentially a CakeML program. And the neat thing about all of these things is that they're verified in whole 4. So essentially, we can think of this as two steps, right? We have the CakeML backend that is already verified by the project. And then we have the Dafny to Dafny IR translation. That's the state we will trust for now. And what we started working on is essentially linking these two parts, going from the Dafny IR to the CakeML AST. And if we zoom in even further, we will see that the Dafny IR is actually living in Dafny. And so to get out of Dafny into whole 4, we will essentially write it as a string, as an S expression. To disk, we will read that in whole 4, the S expression. We will parse it back into the Dafny IR, and now we can actually write the compiler. And as I mentioned before, all of this is done in, so at the end of the day, it's done in whole 4, so we can prove our theorems, semantics, show that they're correct, all that good stuff, and then finally extract the program to CakeML so we can actually get some code that runs. So just to get a better feeling of what this is, I brought some examples. So a very simple, Hello World example looks something like this in Dafny. And in the Dafny IR, it looks like this. At least a couple months ago, it looked like this. It might be a bit different, but I think the key idea should give you at least a feel of how this should look like. But you don't need to look at the details. I'd rather have your attention on the CakeML implementation of this, where the modules in Dafny are essentially translated as structures. Methods become functions, and the print statement is the print statement. You have the some string functions. And the most interesting part is actually exceptions, where we translate exceptions by using, made a mistake. So what I actually want to say is how we translate returns, because CakeML is a functional language, so we don't actually have a return statement, but instead we need to simulate them. And the way we do it is using exceptions, because CakeML or ML do have those. And what we do is essentially whenever we hit a return statement, we just raise an exception and then catch that exception outside of that function. So and return unit, which essentially corresponds to early return. We can do the same technique for loops. We'll see that in a second, or actual return values. So it returns with some values, named returns, and a bunch of other things. So that's all I said. Let's take a look at a slightly more interesting example, which is translating the factorial, an imperative version of the factorial function. And to do that, we will need to be able to translate variables. And we can do this by first taking a look at how it looks in the Dafny IR. At least it used to look, this disclaimer here again, where we first need to declare the variable and then we assign to it. And we model this in CakeML using references. So we initialize a reference, that's what the declaration becomes, and then we can just assign to it normally. Now there's one issue, is that we need to generate an initial value. For integers and booleans, this is not really a problem. But when we think of, for example, user-generated data types, that's already a bit more difficult. But when we think about, for example, type arguments like something of type alpha, it's not really clear what kind of value we could choose here to actually get something that would satisfy the static type checker. I'll leave some discussions about this to the end. So having compiled the variables, we'll need to be able to compile the loops. And those look relatively harmless in the Dafny IR, very straightforward. And the CakeML code looks a bit more intense, but it's really quite straightforward. We translate CakeML, so we translate while loops as Taylor recursive functions in CakeML. And the way it works is just we first check whether the condition is true. If the condition is true, we execute the loop body and then recursively call the function. And as before, we can also still model control flow, like breaks. We can also have support for labeled breaks. And the way they work, again, is the same idea. We just use exceptions. We throw exceptions when we hit a break. And then we have an exception handler, which captures those. But if you look closely in this example, you would probably notice that that break statement is not really necessary, because the exception handler is not really necessary because we never have a break within the loop. But this just goes to show that we currently don't do any analysis on the Dafny AST or the Dafny IR AST or the CakeML produced by this translation process, which is something for future work. So I mentioned before about correctness, right? So how do we prove correctness of this translation step from Dafny IR to CakeML? The first step for that is really defining some semantics. And we define semantics using functional big step semantics, which is a very nice word for just an interpreter, more or less. And so what we can then do is given a Dafny IR program, we can then kind of interpret it and get some results. And at the same time, or after that, we can take the Dafny IR program, we compile it using our compiler, which is written in whole 4, and we get a CakeML AST. And then we can essentially run or evaluate that CakeML AST using CakeML's functional big step semantics. So we have at the end, 2 results, one directly from the Dafny IR and one that comes from executing CakeML or interpreting CakeML by first translating the Dafny IR to it. And what we'll then do or have to do is to prove correspondence. So for example, roughly speaking, if the Dafny IR program returned an integer 3, then the CakeML program better has also returned an integer of 3. And we've already done this for very basic logical and binary operations to just get a feel for it, how it would turn out. So there's still a lot to be done. And for example, here's a list of all the things that are missing still. So synonym types, data types, and I'm sure as time went on, there were more features added to the Dafny IR that we should support. But 2 things I would like to highlight is what I alluded to before, the data types and the type arguments. The question is, how do we initialize variables? Again, for data types, we might get around it with something called the grounding constructor in Dafny. We might be able to smuggle that into the IR somehow. For type arguments, I would assume we probably need to disable the static type checker and then just initialize references with a dummy value. And in case it makes you a bit uncomfortable, it shouldn't, because we're proving correctness anyway. And Dafny guarantees that there's a correct Dafny program, at least in the semantics, that every variable is initialized before it's used. So that shouldn't really be a problem. Another thing that I would be very interested in is looking at how to translate traits and classes into an ML language like CakeML. Because that, while we got away with variables by using references, but for traits and classes, it's not super clear how we would do this. I would assume we need something like vtables, so we use like tuples, function closures, things like that. We probably would need to disable a static type checker again. But again, if you're proving correctness, that really shouldn't be a problem. But beyond, so what is there to be done, right? Beyond just implementing more stuff, right? Because that's always an obvious thing. Extend the feature support. Another obvious thing would, of course, be just prove more things, But these are like kind of going up, like building tall, and building more wide would be something, for example, verifying the translation from Dafny to the Dafny IR. So it's that front end that we kind of trusted should be part of, or could be part of CakeML, where we then define Dafny semantics and show that our compiler from Dafny to Dafny IR preserves the semantics too. And then if you wanted to go super, wide and like super explore new things, one could think of maybe having a representation of boogie in whole 4, and then also essentially verify the whole rest of Dafny, all the proof obligations that are generated by Dafny, they're properly translated into boogie, and then maybe even this SMT requests when they are given to Z3 and we get some certificate, maybe we can check that too, and like more or less have an end-to-end mini Dafny program or compiler or project. But yeah, this is very much just speculation or like ideas on our part. Nothing concrete has been done yet. And with that, I'm done. So thank you very much for your attention. I'm more than happy to take any questions you have.
So thanks for the talk. This seems like a very ambitious undertaking.
Yes.
Do you have a sense for, is the goal to find bugs in how Dafny is doing this? Is the goal to just have a proof of concept that this could be done, or do you see it being kind of a long-term, something that would be used in the long term?
I think it depends on what one wants to focus on. I think you can very much have the CakeML backend as something like, because Dafny already has a bunch of backends, right? It has the C#, the Java backend. So making the CakeML just another backend that has, at the very least, it has the guarantees that once you are in the translated state, you get all the you get like a verified pipeline. So that's, I think, a very practical goal. The end-to-end verification, that's more like a proof of concept and would probably take a PhD or two. I would guess, if you want to do it fully.
Okay, thanks.
Thank you.
Hi. So you mentioned, I guess, like, if you wanted to translate the IR, you said like, well, this works because like it checks the variables are used or they're initialized before they're used. But was that, where did you get that information? Like, is that part of that? Like, that was checked by Dafny in one of these boogie pipeline things, or was that like where, if you were to do a full verification, you would need that information? Where would you get it, and how could you verify those aspects?
I see. So where I got the information that it's always initialized is I think it's in the Dafny in the pro semantics. And and when you verify the boogie, when you verify the Dafny code, it will probably complain. So to answer your question, if I understood correctly, right, for the Dafny to the Dafny AR, that shouldn't really be so it depends how much of the pipeline you want to have in CakeML, right? If you want to have a Dafny to Dafny IR front end, you still kind of need to trust the boogie part that you got a legal Dafny program, right?
So you want to represent the Dafny IR, like that property, as well-formedness of the Dafny IR. So for your purposes, that would be a precondition of your theorem.
Right. And, yes, exactly. So yeah.
And you intend to do the same thing for all of the like precondition, postcondition, all the things that the SMT solver is actually working on in Dafny.
Well, no, I don't think that's quite correct. So I haven't. So this part is really just we just thought about it. We haven't actually done it yet. But the way I would understand it is that there's a set of well-formedness conditions that we have. That is, for example, that every variable needs to be initialized, and then we kind of just assume that that is true, right? So for now, when you give me a Dafny IR, assume you've gotten it from you got it from Dafny Translate, which would fail if you didn't verify it. In the theorem, if we would have to prove that, we would somehow need to express that for the assumption all of these things hold, then you get the correctness statement. But if, for example, this doesn't hold, well, then all bets are off the table, and I guess you'd have some form of undefined behavior. But it's a good question. We haven't thought about this in detail.
Thanks.
Thank you.
Thank you. Could you elaborate a little bit about the strategy for proving correctness between the two output results? I think I read that it's done for basic logic and binary, so I'm guessing like propositional logic equivalence there. But what about for more expressive result outputs? Like in what language is the proof of correctness completed?
So it's all whole for. So it's all written in the whole for theorem prover. So the compiler is essentially a whole function, a higher order logic function that takes a Dafny ASD and creates a compiler ASD. So you have a statement, and it's also in the paper for like a bit more details, which essentially says that if you started in some equivalent state and you pass that to the Dafny IR semantics, and then you compile it and have the CakeML and you pass that, then you get a new state. One that was generated interpreting Dafny code and one from CakeML code. Then these two states have some correspondence. I'm being very vague on what this correspondence means, but this is just like one theorem that you can, that's a simulation theorem that you can prove and that we start to prove in whole for. So everything lives in whole for, really. Yeah.
Thank you.
I hope that's answered the question.
Let's thank the speaker again.